So if you're happy, what does that mean? Like it's just really funny because a couple days ago I was talking with somebody and they're telling me that somebody that they tutored, they were like, you know the nursery rhyme, like if you're happy and you know it, clap your hands. Um, and apparently this kid was like, but what if you're not happy? And I'm just like, that's the saddest story I've ever heard. Like, if you're a kid and you and everybody else is singing, if you're happy and you know it, clap your hands, and you're just like, but what if you're not happy? Right? Like, that's the funniest thing ever. And then I was joking with my friend about this, that like, oh, that's an opportunity to teach them about like uh, like some rectangles are squares, but not all rectangles, or not all squares are rectangles. I got that backwards. All squares are rectangles, not all rectangles are squares. Right? Like, okay, if you're happy and you know it, clap your hands. But we're not telling you what to do if you're not happy. So you can clap your hands. You're still allowed to clap your hands, but you don't have to clap your hands. I thought that that was really funny, and it came to mind because of the second part of this title. Some scary books are huge. And I kept struggling in my prior video where I talked a tiny bit about how some scary books are tiny, right? I wish I had... Yeah, no, I have it over here. One sec. So, a couple of videos ago, I told a joke or idea. I don't even know if it's a joke. It's a little... yeah, anyways. It's a thing. Some of the scariest books ever are tiny. The smaller books get in math, like it should raise your alarm bell, your alarms in your head that this might be a terrifying book. But then other books, I should have grabbed the other one just now, but some other tiny books are perfectly happy. Right? Like, if you're happy and you know it, clap your hands. If you're tiny and you're scary, clap your hands. I don't know. Like, this one doesn't have any exercises in it at all, and it's like the book that some other ones use. I haven't actually read it yet, but I know that that's a scary book. And I did want to follow up because I struggled to actually find the page. The first sentence of this book, A Course in Arithmetic, is... Okay, well, the first sentence isn't that bad. Let K be a field. The image of Z in K is an integral domain, hence isomorphic to Z or to Z slash PZ, where P is prime, semicolon. Its field of fractions is isomorphic to Q or to Z PZ equals FP. What? It's been a while. It's been a minute. But I'm actually happy that I do understand that a little bit more than last time I read that. Anyways, so if you're happy and you know it, clap your hands. Some tiny books are scary, but not all tiny books. So, let's do it this way. Because there was this other part of the joke with my friend that was like, oh, you could teach them about biconditional inference, or like if A, then B. If you have a square, then you have a rectangle, right? But that's different than saying if B, then A, right? If you have a rectangle, then you have a square is false, right? So if you're happy and you know it, clap your hands. If you're not happy, we're not going to tell you what to do. Like, you can still clap your hands. It's not an if and only if. But then, yeah, the other thing that came up was like, you could have if you're happy, but then there's also know it, right? Like, don't forget that this is a 2x2 quadrant, or 2x2 grid here, matrix. So if you're happy and you know it, clap your hands. Clap your hands. Otherwise, if you're not happy, you can still clap your hands if you want to. I don't know. This is undefined. What if you're happy and you don't know it? Like, you don't even know that, right? That's one that you're not thinking about. What if you're not happy and you don't know it? What if you're not happy and you know it? Etc. So, if you want to learn more about this, there's a great video called, I think, what is it? Ideology? It's something like that. I feel that that's not it, and it's another word with I, and it's going to come to me, but it's by Gary Bernhardt, and it's about software, and it's fantastic. Anyways, this is a math stream. Let's continue. So here's my tables of... oh, wait. There's one more. Let's finish this thought. Some tiny books... Some scary books are tiny. Some scary books are huge. This one is also scary as hell. Like, if you try to seriously work through this book, this is Lang, Serge Lang's Algebra book. This one is notoriously scary as well. If you try to work through this book, yours is going to look like mine, just like this, I think. So, my teacher said that, and I was like, no way, I'm going to take care of mine, and then this happened. It still happened, even though I tried. I tried to work through this during the pandemic, and as I said, I was also working through Dumb It and Foot before. So we're going to try to get the formal definition of a vector space from Strang, from Axler, maybe from Shilov, and I definitely want to write down the definition of a vector space according to this guy. So, anyways, let's continue. This is a math practice stream, and the point is to solve every math problem ever. I'm a hobbyist, so I'm not going to get in any kind of academic trouble for doing this. We've done problems 1 through 11 in Strang. I've also done problem 13 and 14. I think that I struggled a little bit with 14. I think that one was on stream, and I didn't read 12 very carefully. It confused me, so I moved on. And then I think on stream we did Axler 1 and 2. And this morning I woke up kind of early, and I think it was just 3 and 4 that I just solved on my own. It might have been 2, 3, and 4. I forget. And then on my own I've done Shilov, and then I showed those exercises as well on stream. So let's get going. Let's keep going. Last video, I showed this as Axler 2, 1A2, and we are showing that addition is associative in the complex numbers. And so here's the solution. So if you want the solution, you could either copy me or you could ask ChatGPT. And yeah, like, Axler keeps writing lambdas everywhere. Like, we get it. You love Haskell. Okay, we get it. I do too. Typically gamma is the third Greek letter, not lambda. So I'm going to use I'm going to use gamma instead, but that doesn't change too much. So here is, I just worked 1.18.3 this morning, and so we're also showing associativity of multiplication in the complex numbers. And basically, so you set it up, I'm using A1, A2, and A1 and A2 for alpha, B1 and B2 for the coordinates of beta, and C1, C2 for the coordinates of gamma. I think that works out nicely. Axler's book seems to want to use A, B, C, D, E, F. I would find that very confusing because as you go through this, I would find it pretty confusing and I'd have to be double checking, like, is D part of beta or is D part of gamma? Like, I don't know. So basically, here's the important part. A1, B1, C1 is the same as A1 parentheses B1, C1 in the associativity of multiplication in the real numbers. So we're defining the complex numbers as a pair of real numbers, and it seems like we're allowed to assume commutativity, associativity, and those nice properties that we're used to in the real numbers. I wrote out my thought process as I was doing this. Like, this problem is a little tedious. It's just tedious is the thing. And so I got bored. I got quite bored, and I just started doing ... I was like, okay, I wrote out everything in terms of the... I wrote out the real part. The real part of these numbers is in the large bracket, and then the imaginary part it's similar. It's like just super similar. And then, yeah, I got bored, so I just moved on. I wanted to say that somebody like Shilov, or definitely Lang, their proof would just be by the associativity of addition in R. Oh, wait, we're talking about... Well, yeah, I mean, associativity of addition and... I guess we do need both. Associativity of addition and really multiplication. No, this is all multiplication. What am I talking about? This is really all multiplication. They would literally... This wouldn't be a problem. But it would be a very brief sentence in the text that's like, it's trivial that the complex numbers have the same properties as the real numbers, or something. It's trivial, or it's an exercise to the reader to verify associativity and commutativity of the complex numbers, or R, maybe something like R gives rise to the associativity of you know what I'm saying, sort of, maybe. You probably don't know what I'm saying. The associativity of multiplication gives rise to associativity of multiplication in C, in the complex numbers. I don't know. I'm losing the plot on that one. And yeah, basically, distributivity, like the distributivity, the distributive property that you can multiply lambda times alpha plus beta couple things that are weird to me about that. I would write that alpha beta plus gamma, but you do you. That the distributive property holds, that this should be alpha beta plus alpha gamma. And I'm just going to take Shilov's answer, is that it's because it's the same thing in the real numbers. Like, just, that's it. And that's good enough for me because I'm a hobbyist. So let's move on. Next problem. What are we doing? I want to make sure we solve one problem from Axler. Oh wait, do we want to solve a problem in Axler? I feel like we just did. Let's get some more. Let's get some more computational examples. Let's work some easier problems. So let's go back to Strang and skip forward if you want to see the formal definitions of vector spaces. I just want to make sure, because I do have a time limit today, I want to make sure that I solve at least one problem, because the point of this stream, the point of mathematics, the way that you get better at mathematics is solving problems. You can't just read. You can't even just take notes. That's not enough. You have to solve lots of problems, everybody. I wish I understood that better when I was in undergrad. I shouldn't say when I was in undergrad. I should just say when I studied math, because I did not go to graduate school. So that explains a lot of the issues that we're going to come across today. What is Strang? What problem are we working from Strang? So we're going to do Strang 15. 1, 15. Suppose the 12... Oh, yeah, we're talking about the clock right now. Suppose the 12... Oh, I think I solved a couple of Strang problems on my own. So, yeah, because these are... I already drew the clock, and... where did I do this problem? No, I did this yesterday. Yeah, I did this yesterday on stream, but it's good to show it again. So here's this clock. We can try to lift this thing. Lift it to the other page. We had this other problem that was asking, like, what if you added all of these vectors together, starting from the center of a clock to each of the hours around the 12 hours of a clock? Well, the sum is going to be 0 because each vector is going to cancel the opposite one out. Like, for example, the vector to the 1 o'clock is opposite. It's the exact same angle or direction as the vector that points to 7. So it's like two different forces that cancel each other out, and they just zoop back to the center, right? That's if you added all of them together. Now, this problem is asking something else, and I haven't looked at it yet. Suppose the 12 vectors... 1, 15. Oh, there it is. Okay, suppose the 12 vectors start from 6 o'clock at the bottom Oh, okay, cool. Now this is getting a little bit more interesting. I feel like the last couple of problems I was like, this is this is not super interesting, sir. Now this is a little bit more interesting. All right, so suppose the 12 vectors start from 6 o'clock at the bottom instead of 0, 0 at the center. Cool. Okay, interesting. The vector to 12 is doubled to 0, to 0, 2. Ooh, interesting. Okay, I don't know this one. The new 12 vectors sum to, well, it says adds to the sum of the, well, whatever. The new 12 vectors add to blank. Okay. All right. I may not be able to figure this one out. Let's see what happens. All right, so everything's starting from 6 instead of from the center. And so it's saying that, like, let's draw the tick marks around a clock. Interesting. Okay, and we have arrows that are pointing in each direction. I think that I'm misunderstanding one point from the premise. Yeah, I think so. Let's see. Yeah. Okay, so I don't know where it states it exactly. Yeah, it wasn't very precise on how long the vectors were in the original clock. It didn't say anything. It just has this drawing from the center of a clock, quote unquote, around a circle. So because of the definition of a circle, we know that all of these arrows, like the definition of a circle is the set of points of equal distance around a point. Like that is the definition of a circle. So we know that all of those arrows, all of those vectors have the same length. But now on this one, it doesn't exactly specify whether we're thinking about this. My drawing is a little sloppy, y'all, so please imagine what I should be drawing instead. You see what I mean? Where, like, the arrows... this is not what he meant. I'm pretty confident on that. Right? Like, kind of fanning out, etc., etc. I don't think that's what they meant. What they meant was that all of them still have unit 1, or like length 1, but now they're all transposed down starting from the 6 o'clock point, I think. We should use a different color. Let's use a different color so people can see it compared to the original. How's it going? If folks are enjoying this, please let me know. If you see this video after the fact, drop a comment in the comment section. I hope that this is enjoyable. It's a little weird, but I think that it could be fun. I think it could be a fun thing, especially if we can form a community here of people practicing mathematics because it's fun and beautiful instead of because it's an assignment. Okay, so now we have like a new circle. I'm going to use this to help me draw arrows of length 1. I think that's a coincidence that they matched. I don't know. Maybe it's not. Okay. All right, so we moved all of the arrows. We're taking the perspective that these are all length 1 arrows. Whatever. And we're just moving them down to the 6 o'clock location on the clock. And then the problem states, what do you do if the, what happens if that bottom, if the arrow pointing to 12 o'clock is doubled, if the length of that vector is doubled, then it's going to point all the way up to 12 o'clock. Okay, so now what do the sum of the vectors add up to? Well, I think it's going to sum to 1. The sum of the vectors vi from I equals 1 to 12, that is, if we're very careful. The sum of the vectors vi is going to add up to a vector of length 1 pointing north. How do we make that precise? How do we state that more clearly? That is going to be really the vector 0, 1. Like, if this origin is 0, 0, and the reason that we can see that is that this first half of the vector is annihilated by the vector pointing in the opposite direction, but then we still have that remaining green part left. So, yeah. I don't know. Exercise to the reader. Make that more precise. We're done. All right, we solved one problem. Great. Let's check chat. How's it going? Oh, hey, Alok. How's it going? How are you, man? Hello. I'm going to go and eat my dinner. Bye for now. Well, dude, thanks for stopping by. I'm sorry I missed your chat. I'm sorry I missed it. I'm going to come back soon. Cool. Thanks for stopping by. It's really nice to have company while I do this. Great. Now let's keep moving because I definitely have to go in 20 minutes. Let's actually complete this goal, which has been the formal definition of a vector space. According to Strang. Axler. Shilov. Yeah, we need a color for Lang. Shilov is red. Red is hard at least in American culture. You can also think of green, yellow, red as like the stoplight. Like our stoplights are green, yellow, red, right? Red is like stop or hard. It's pretty often red is hard. So we need something harder than hard. Um, I'm going to use this color for Lang. Let's try to move it up. It's also red. That's not quite what I'm looking for. Let's get a slightly... Let's see, can we make it a little... How do we make it a little muddier? Well, I'll play with this. It's going to be something like that, maybe. I think we need like a little bit more brown tone for what I'm looking for. But it's going to be good enough for now. Oh, shoot. Oh, I see. I thought it was modifying the last one. All right. Sorry for the aside, y'all. This is not good content yet. I don't know. It's going to be something like that, I think. I don't know why it looks like there's some opacity on that color, but anyways. Lang. We need more brown. But, yeah. Let's do it. This is bothering me. I had a goal, and we're almost there. Yeah, it just looks like there's opacity, and that's not what I wanted. I wanted a little bit of brown, all right? Shilov and Lang. Lang is the color of dried blood. That's what I'm going to call it. We want the color of dried blood. Maybe Shilov is like coursing, healthy, life-giving blood. Lang is going to be the color of dried blood. Let's move on. Strang. What are we getting from Strang? What are we getting from Axler? What are we getting from Shilov? And what are we getting from Lang? That's dark. That is a dark joke. I apologize. That didn't come across the way I wanted, but whatever. Let's just move on. Formal definition. And I just got thrown off by this color. I wanted like a copper tone, and I thought that the color I already had was going to be good, but it wasn't. Let's move on. So from Strang, I found... Oh, no. It's on my other computer, isn't it? Okay. Give me a minute. Let's find let's find the PDF of Strang, because I had it. My copy is still in the mail. PDF Strang, linear algebra done right. I found one very recently that worked pretty well for me. Oh wait, why am I getting... Oh, whoops. Linear algebra, not linear algebra done right. I mixed the two. It's funny, like, Axler's book still pops up when you search for Strang. Like, the two are just such... I feel like they're just the two most recommended books. Like, if you look for recommendations today, like modern textbooks for a first and second course in linear algebra, I think that Strang is by far the top recommendation for a first course. For second course, there's a lot of different recommendations. Axler is very commonly recommended. I haven't seen Shilov recommended much, but I think it's just because it's a little bit older. Friedberg, Insel, and Spence. That's the one that I used in my graduate linear algebra course that I took. And it was nice. Like, I liked that book. Yeah, I I don't have it with me, but I wish I did because I think it was a really, really great book. Um, yeah, Axler takes a very different approach, which is really unconventional, and I look forward to it. Um, Axler focuses on theory, and he really focuses on theory and focuses on building all of linear algebra without the determinant. Like that's his life's mission. If you just read on the internet, like that's his yeah, his book is just very famous, I suppose, and I'm sure he's done a lot of other really great, brilliant math, but his name is really closely attached to that book. And the title, which is very, bold, let's say, Linear Algebra Done Right. Like, the right way to teach linear algebra is without the determinant. Exercise 1 of Shilov is about the determinant. So clearly it's like an unconventional, different approach. But yeah, I keep reading again and again that both of these books are works of art. Like Strang's book and Axler's book. They're both just very, very highly recommended. And for Axler, being able to create the entire theory and prove all of the prove everything about all the important results about linear algebra without the determinant is apparently pretty elegant, and I look forward to learning that and seeing it. So here's the one that I found. Let's get definition from each of these folks. Oh, Strang doesn't do it for a while. Oh, yeah, he doesn't do it for a while. Okay, he does in chapter 3. Yeah, section 3.1. Chapter 3, page 85. Okay. My course, I think, was really similar. My undergrad course was very similar. We spent the first few weeks doing matrix calculations and learning how to use matrices to solve systems of equations. And that's why I introduce it the same way. I introduce the concept with the familiar examples from college algebra or high school algebra. You have two equations and two unknowns, and how do you solve that? That is tremendously useful in all of industry, like especially artificial intelligence. Artificial intelligence is just solving lots of linear equations, sort of, kind of. Okay. Yeah, okay, I like it. So, Strang is not written for math majors, which is great. That's beautiful. Like, Strang is written for everybody taking linear algebra for the first time, including math majors, but it doesn't have the level of like formalism and the level of rigor, I suppose, and he doesn't claim for it to. He does not even call it the definition. Like, he doesn't say, like, definition, a vector space, blah, blah, blah. There's a circle, like an oval around this. Requirement. All linear combinations CV plus dw must stay in the vector space. Everywhere here we're defining a vector space, so I'm going to use VS for short throughout, because otherwise we're going to be here for a while. Requirement. Number 2, the row space of A is quote unquote spanned. Spanned by the rows of A. The columns of A span the columns of A span C of A. Okay. All right. I think that I'm going to have to figure out what he means by that. I know most of that, but the last little part is a little interesting to me. I think he's restricting everything to the complex numbers instead of, matrices MI or M1 to MN. I'm seeing this for the first time. This is a reaction channel, y'all, in a sense. And functions F1 to Fn span. Okay. I'm feeling like that dog that's just like, I don't know what's going on, or whatever that meme is. You know, that meme of like a dog at a computer or something. All right, this is not what I was expecting. And cool. Neat. Is there somewhere else where he defines some things that I'm missing? Yeah, there's like a lot of metaphors that he uses, and that's cool. Okay, all right. I'm going to come back and understand that a little bit more later. Let's find a dang orange color. How do I get orange? I guess this one is orange. Yeah, that's orange. You get my joke. It is orange. If we get to it, we're going to get to Lang. Alright, so that's Strang's definition of a vector space. Let's see what Axler calls it. Let's check chat. How's it going? Anybody out there? Anybody out there? Isn't that's like a Pink Floyd song or something, right? Where'd it go? Too many windows, too many tabs. This one? Yeah, okay, good. Nobody's there. Or not good. I wish somebody was there asking good questions, but I'm glad that I didn't leave anybody hanging, is what I'm trying to say. Linear algebra done right. So something that's wonderful about linear algebra done right, I'm not able to put it up on screen right now because it's like bright white, and I don't personally like having like a huge bright white thing on a video. So next time I'm going to try to invert the colors of the PDF and have it on screen. Let's see. I think that it's section 2, like page 12 of Axler. Okay. I think that we need... Yeah. Okay, so Axler's is like... Yeah. Axler is nice. I think it's nice. 119, definition. It's still, like, not nearly as dry as, like, the graduate books. It's, like, nowhere near as dry as those. For better or worse. Addition and scalar multiplication. All right, so we need to define first what addition is and what scalar multiplication is. Okay, and I'm going to write this out formally, or like verbatim, I mean. An addition on a set V is a function. Am I running out of time? Oh, damn it. Yeah, I am running out of time. Is a function that assigns an element u plus v in the space to each pair of elements Okay, I'm going to take some shortcuts. A scalar multiplication is some stuff. Look it up yourself. 120, definition of a vector space. Here's the important part, y'all. Definition of a vector space. Let's get this written down, and then I probably have to go. I wish I could write down Lang's today, but I think we're not going to get there. A vector space, oh, I could just show it to the camera. Lang's. A vector space is a set V along with an addition on V and a scalar multiplication on V such that the following properties hold. All right, so we are going to require commutativity, associativity, we're going to require an additive identity. We're going to require an additive inverse. We're going to require a multiplicative identity. And distributive properties. And then that's it. And then that is the definition of a vector space. Anything that follows these rules. So, for example, commutativity is u plus v equals v plus u for all vectors u and v. Associativity is u plus v plus w. Equals u plus v plus w. Additive identity is that there exists 0 in v such that 0 plus v equals 0 for all v, for all vectors. Additive inverse. This fancy symbol is for all v. There exists w such that v plus w equals 0. That's basically subtraction. So I called it that a couple of streams ago. Multiplicative identity, 1v equals v for all vectors, and distributive properties, u plus v equals au plus av. All right, we're running out of time. So last thing I want to do, Shilov is going to be the same exact thing. Shilov is going to use fewer words. I already skipped a lot of words of what Axler has. But let's see what Lang says. Where is it? I was looking this up again earlier. And I think I said it last time, too. Damn it. I'll be late to the thing. It's fine. Chapter 3, Section 5, page 139. Page 139. Ooh. A module over a field is called a vector space. That's it. That's his definition of a vector space. Okay, all right, that's cheating. What is a module over a field? So I introduced the idea of a field before, so I'm not going to find that definition today. But basically, it's any set of numbers that has multiplication, addition, subtraction, and division. Modules, page 117. Modules. Let A be a ring. What's a ring? Okay, we don't have time for that. A left module over A, or a left A module M, is an abelian group, usually written additively, together with an operation of A on M, viewing A as a multiplicative monoid by Ri2, such that for all AB in A and XY in M, we have A plus B times X equals AX plus BX, and A times BX plus Y equals AX plus AY. We leave it as an exercise to prove a couple of things. In a similar way, one defines a right A module. We shall deal only with left A modules, and we'll just simply call these modules. Let's get it on camera, and then I gotta go. So, thank you everybody for watching this. This was fun for me. I gotta run. Let's get this on camera because it's beautiful. Oh, air server disappeared. Oh, damn it. I wonder how much we lost. Basic definitions. Let A be a ring. A left module is blah, 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 blah. Did we completely lose all of this written, beautiful stuff because I didn't have air server running? I'm so annoyed. Oh, well. Oh, well. Former definition of a vector space according to a few different perspectives. According to Strang, Axler, Shilov, no Shilov, and Lang. Strang, requirement, all linear combinations, stay in the vector space, row space, something or other. Axler is a lot more precise. And then Lang just wants to make you feel bad. Thanks for watching. My name is The Math Hobbyist, and I had a lot of fun today. Like and subscribe. And